So today I want to tell you a little bit about identical synchronization of non-identical oscillators. Most of the results of this talk is based on a publication Adilson and I recently published in Nonlinearity. So in particular, I want to ask and hopefully answer the following three questions. First, can non-identical oscillators ever synchronize identically? And if so, can we analyze the stability of this identical synchronization state when the difference between the oscillators is not small? Furthermore, can oscillator heterogeneity ever induce synchronization instead of destroying it? Let's begin with a brief review of identical synchronization of identical oscillators. A network of diffusely coupled identical oscillators can be described by the following dynamical equations. Here, xi describes the d-dimensional state of the ith oscillator. F is a function that describes the intrinsic dynamics of the oscillators. Sigma is the coupling strength. And because the network is diffusely coupled, its structure is described by the Laplacian matrix L, and H would be the interaction function. Identical synchronization refers to the state in which x1 equal to x2 equal to xn for all time t. Visually, it looks something like this. Now, how do we analyze the stability of the identical synchronization state? We need to calculate the maximum transverse Lyapunov exponent of the variational equation. So the variational equation is an n times d dimensional equation that describes the evolution of the infinitesimal deviation delta x from the identical synchronization state. It can be difficult to analyze for large networks because the dimension of the equation grows with the network size n. What we can do is we can find better coordinates under which the Laplacian matrix L is in diagonal form. This would enable us to decouple this n times d dimensional equation into n independent d dimensional equations that can be analyzed much more efficiently. This is the essence of the master stability function formalism, which enables us to study the synchronization stability of any networks of identical oscillators. Now we're ready to look at the non-identical oscillators. The dynamical equations look almost exactly the same as the one for the identical oscillators, except now we have an additional subscript I on the F. We also specify a set of m different functions that describes m distinct intrinsic dynamics, and each fi would be chosen from this set of different functions. Now, in order for those non-identical oscillators to synchronize identically, they have to share a common orbit S that the system can synchronize on. But different fi can have different dynamics outside this common orbit. So now, if we look at the variational equations, it looks very much the same as the one for the identical oscillators, except the first term here inside the parentheses is more complicated because we have to specify which oscillator takes which function as its intrinsic dynamics. This information is provided by some additional matrices Dm, which are diagonal matrices whose ith diagonal entry is 1 if and only if the ith oscillator chooses the m's function as its intrinsic dynamics. Now, what we end up with is still an equation of n times d dimensions, which can be hard to analyze. But what we want is to find better coordinates under which we can decouple these variational equations as much as possible and reduce its complexity. So unlike the case of identical oscillators, it is generally impossible to find a basis that can simultaneously diagonalize all those matrices D1, D2, Dm, and L. Instead, what we can do is to find a transformation that simultaneously block diagonalize those matrices, and the variational equation will be decoupled following the common block structure of the transformed matrices. There are efficient algorithms that can find the finest simultaneous block diagonalization of any set of matrices, which we call the SBD transformation. And because it works for any set of matrices, the SBD transformation can be applied not only to diffusively coupled systems, but also to systems with adjacency matrix coupling, delay coupling, or some other coupling. So as an example, let's look at this wheel network of 16 nodes on which there are two types of different oscillators that are arranged alternatingly. Its variational equation looks something like this. The first two matrices would be D1 and D2 that describes the alternating arrangement of the oscillators. And the third would be the Laplacian matrix that describes the network structure. You can see easily that there's no common block structure shared between those matrices. So the whole equation is coupled together and would be hard to analyze. But if we apply the SBD transformation, we would get three new matrices that have a very fine common block structure, and accordingly, the variational equation would be very much decoupled and much easier to analyze. So one major motivation behind the development of this framework is a new phenomenon called asymmetry-induced synchronization, or AlSync. It refers to a scenario in which a network of oscillators must become non-identical in order for them to synchronize. More specifically, we observe AlSync if all homogeneous systems of identical oscillators are unstable, and at least one heterogeneous system composed of non-identical oscillators can synchronize stably. AlSync was first discovered in 2016 for phase amplitude oscillators by Takashi Nishikawa and Adeson model, and later shown to be prevalent in multi-scale systems with chaotic dynamics by the same authors and myself. In this talk, I want to convince you that AlSync can also be prevalent in delay systems. As an example, we studied the delay-coupled Stuart-Landau oscillators. So here, Zj would be a complex variable that describes the state of the jth Stuart-Landau oscillator, and its intrinsic dynamics f has three parameters: lambda, omega, and gamma. Lambda relates to the amplitude of the oscillation, while omega and gamma relates to the angular velocity of the oscillation. If we assume that the oscillators synchronize on a limited cycle, then we can solve for the amplitude R naught and the frequency omega from the equation 1a and 1b. And what we can learn from the highlighted part of equation 1b is that if we replace omega by omega plus h and replace gamma by gamma plus h over R naught squared, where h would be an arbitrary real number, then the synchronous state would remain the same. In other words, we have an entire family of non-identical Stuart-Landau oscillators parameterized by h that can synchronize identically. And from this family of non-identical Stuart-Landau oscillators, we take two different oscillators, F1 and F2. F1 has its parameters modified by a fixed positive h, and F2 has its parameters modified by a fixed negative h. And we place these two different oscillators on a directed ring of 6 nodes. This gives rise to two possible homogeneous systems whose stability is shown as a red line and as a cyan line in this plot. You can see that after h becomes larger than 0.3, both of them becomes unstable in the sense that the maximum transverse Lyapunov exponent becomes positive. On the other hand, the most stable heterogeneous system, whose network diagram is shown here, and whose stability is shown as the blue line, it remains stable for the entire of H studied here. This gives us a wide range of AlSync phenomenon. But of course, this is only for a small network with a particular set of parameters. You might ask, how generic is this? We also have plots showing that AlSync, which is shown as a orange region here, is very common for even for very different coupling delay tau, and we have many other similar plots showing similar results for different network structures in our paper, which is also available on arXiv. To conclude this talk, I want to share with you an animation showing AlSync in larger systems of Stuart-Landau oscillators. So here we have 4 systems, and each dot is a Stuart-Landau oscillator. What you will see in the animation is that the homogeneous systems becomes unstable, and we would switch the two off-diagonal systems to become heterogeneous systems in the middle of a simulation. And you can see that they would converge back to synchrony, either to the fixed point or to the limit cycle. So I hope you can all see the video now. So at first, we have 2 different homogeneous systems, which are currently slowly desynchronizing. And at the middle, we switch the off-diagonal ones to heterogeneous system. And you can see both of them synchronize either to the fixed point or to the limit cycle. And let me just show you a little bit slowed down version, which happens right at the transition. So this right before we switch the off-diagonal ones to heterogeneous. And you can see that they very swiftly, they synchronize very swiftly to identical synchronization. And with that, I want to thank you for your attention.